Directly updating a database while simultaneously sending a message to a broker is a recipe for data corruption in distributed systems. Use the transactional outbox pattern to ensure every business state change and its corresponding event are committed atomically. The dual write problem occurs when an application successfully updates a database but fails to publish a message due to network interruptions. This results in an inconsistent system state where the rest of your architecture is unaware of the local change. The transactional outbox pattern solves consistency issues by using a local table to store events. Both the business record and the event record are saved within the same database transaction, guaranteeing that either both succeed or both are rolled back. Create a dedicated table named Outbox in your Postgres schema. This table acts as a temporary buffer for events that need to be propagated to other services. It must be part of the same database used for business data. Include columns for a universally unique identifier, an aggregate identifier, and the event type. These fields allow downstream consumers to identify the source of the change and the specific entity that was modified within your application domain. Store the event data in a binary JSON column to provide flexibility for different message structures. This allows you to evolve your data schema without modifying the outbox table definition every time a new event type is introduced. Add a destination column to specify which message topic the event belongs to. Include a timestamp or a sequence number to ensure that the order of events can be reconstructed accurately by the consuming services during processing.
In your application code, wrap the business logic and the outbox insertion in a single transaction block. This ensures that the message is only available for streaming once the primary database state change is safely committed to disk. Postgres logical decoding provides a stream of row-level changes by decoding the contents of the write-ahead log. This mechanism allows external tools like Debezium to capture insertions into the outbox table without performing expensive polling queries. The write-ahead log is a sequential record of all changes made to the database. By reading this log, Debezium captures every insertion into the outbox table with minimal latency and negligible impact on the performance of the primary database. Create a logical replication slot in Postgres to track the progress of the change data capture process. The slot ensures that the database retains necessary write-ahead log segments until the Debezium connector has successfully acknowledged their consumption. Define a publication that includes only the outbox table. Restricting the publication to specific tables reduces the volume of data sent over the network and prevents the exposure of sensitive business data that does not need to be streamed. Debezium runs as a connector within the Kafka Connect framework. It acts as a bridge that monitors the Postgres publication and transforms database change events into structured messages that are then published to specific Kafka topics for downstream use. Configure the Debezium Postgres connector by providing the database hostname, port, and credentials. You must also specify the name of the logical replication slot and the publication created in the previous steps to establish a stable connection.
Set the plugin name property to pgoutput in the connector configuration. This is the standard logical decoding plugin for Postgres versions 10 and higher, enabling efficient communication between the database engine and the Debezium connector runtime environment. The snapshot mode determines how Debezium handles existing data. Setting it to initial allows the connector to perform a full read of the outbox table before transitioning to streaming new changes from the write-ahead log in real time. Once the initial snapshot is complete, Debezium switches to continuous streaming mode. It monitors the outbox table for every new commit and immediately emits a corresponding event to Kafka, achieving low-latency integration between your services and data stores. Single message transformations allow you to modify events as they pass through Kafka Connect. In the outbox pattern, these transformations are essential for flattening the database change envelope and extracting the specific business payload required by consumers. The Debezium Outbox Event Router is a specialized transformation that recognizes the structure of an outbox table. It automatically extracts the payload column and uses other column values to determine the Kafka message key and destination topic. Configure the transformation to use a column like aggregate type to route messages to different topics. This dynamic routing allows you to organize events logically, such as placing all order events in one topic and user events in another. Map the aggregate identifier column from your outbox table to the Kafka message key. Consistent keys are vital for maintaining the order of related events within a single Kafka partition, ensuring that updates to the same entity are processed sequentially.
Extract the contents of the payload column so that the resulting Kafka message contains only the relevant business data. This prevents the internal database metadata from leaking into your event stream and simplifies the logic required for downstream consumers. Integrate a Schema Registry to manage the structure of your event payloads. By validating messages against a registered schema, you ensure that producers and consumers remain compatible even as your data models evolve over time in a distributed environment. Use Avro serialization for your Kafka messages to achieve high compression and strict schema enforcement. Avro is more efficient than plain text formats and provides a robust way to handle field additions and deletions while maintaining backward compatibility. Consumers must be impotent to handle the possibility of duplicate messages. By tracking the unique event identifier in a local store, the consumer can detect if it has already processed a specific message and avoid executing the same logic twice. Implement duplicate detection by storing processed message identifiers in a high-performance cache or a local database table. This check is critical because network retries and connector restarts can occasionally result in at least once delivery semantics in Kafka. Optimize throughput by adjusting the batch size and the poll interval settings in the connector configuration. Larger batches increase efficiency by reducing the number of round trips between Kafka Connect and the database, but may slightly increase individual message latency. The database user for Debezium requires specific privileges, including the replication attribute and select access to the Outbox table. Ensure the user also has usage permissions on the schema to allow the connector to query metadata and read the log.
Set the PostgreSQL configuration parameter for the write-ahead log level to logical. This setting is mandatory for change data capture because it instructs Postgres to include the detailed row changes necessary for Debezium to reconstruct the table modifications. Verify that the maximum number of replication slots and wall sender processes are sufficient to support your connectors. Running out of these resources will prevent Debezium from starting and can block other replication tasks within your database cluster infrastructure. Enable heartbeat messages in the Debezium configuration to ensure that the replication slot progress is updated even during periods of low activity. This prevents the write-ahead log from growing indefinitely and consuming all available disk space on the database server. Monitor the replication lag to identify potential bottlenecks in your event pipeline. Large lag values indicate that the connector cannot keep up with the volume of changes, which increases the delay between a database commit and the corresponding Kafka message. Configure alerts for the state of the Kafka Connect tasks. If a task fails due to a network error or a malformed message, it must be restarted promptly to resume event streaming and prevent the Outbox table from growing excessively large. Implement a background process to delete processed records from the Outbox table. Since Debezium captures changes from the log, the physical rows in the table are no longer needed once they have been successfully streamed to the Kafka broker for distribution. Use a scheduled job or a database trigger to remove old Outbox entries based on their age or a processed flag. Keeping the table size small ensures that write performance remains high and that disk usage remains predictable over long periods of operation.
Configure dead letter queues in Kafka Connect to handle events that fail the transformation process. This allows you to isolate problematic records for manual inspection without stopping the entire event stream or losing data during the integration process. Set the error tolerance property to all to prevent a single bad record from halting the connector. Combine this with the dead letter queue to ensure high availability while maintaining a record of failures for later troubleshooting and correction. Place the Postgres database and the Kafka Connect cluster within the same network zone to minimize latency. Use encrypted connections to protect the data stream as it moves between the database and the message broker through the Debezium connector. Remember that while the Outbox write is atomic, the overall system is eventually consistent. There is a small delay between the database update and the message arrival at the consumer, which must be accounted for in your application design and user experience. Never include calls to external web services inside the database transaction that writes to the Outbox. External calls introduce latency and can lead to long-lived locks that degrade database performance and cause connection pool exhaustion under high load. Include a version field in your event payload to facilitate schema evolution. This allows consumers to identify the structure of the data and handle multiple versions of the same event type simultaneously during transition periods between software releases. If your application supports multiple tenants, include a tenant identifier in the Outbox table. This allows you to route events to tenant-specific topics or filter them based on organizational boundaries within your shared infrastructure.
For very large payloads, store a reference link in the Outbox table instead of the full data.
The consumer can then use this link to fetch the actual content from an object store, preventing Kafka and the database from becoming overloaded. Verify your implementation by simulating database restarts and network partitions. A resilient Outbox setup must ensure that no events are lost and that the Debezium connector resumes correctly from the last acknowledged offset in the write-ahead lock. Combining Postgres atomicity with Debezium change data capture creates a robust foundation for distributed enterprise integration. By mastering the Outbox pattern, you eliminate the risks of data inconsistency and build a truly resilient event-driven architecture.